SwayamPrabha. Digital India. Educated India.
Dear learners, greetings from IIT Guwahati. We are in the MOOCs course Advanced Thermodynamics and Combustions, Module 6, Chemical Kinetics. In this module, we have 3 lectures. One is Fundamentals of Chemical Reactions, where you have covered the basics of chemical kinetics. Second one is the reaction mechanisms. Here also, if we have seen what are the different possible reactions, global reaction, elementary reactions, how they need to be addressed, and also we elaborated the concept of chemical time scale. And in today's lecture we will be considering reaction mechanisms, and it is mainly and it is part 2 of this reaction mechanism. It is mainly dealt with the practical considerations of some reaction systems. So, this is the summary of this today's lecture, and here in this lecture number 25, that is reaction mechanism part 2, first we will introduce the concept of chemical kinetics with global and elementary reactions, and then we will look into the equilibrium products of combustions, which we have discussed earlier. Now, in this lecture we will try to focus on very specific chemical mechanisms that are of interest for combustions. First one is the very common phenomena which is used in the rocket propulsion systems, and it is called as hydrogen oxygen reaction systems. Then the another one is carbon monoxide formations. When we have when in the IC engines, when the fuels are not burnt completely, and it makes the formation of carbon monoxide. Then there are also issues of formation of nitric oxide, NOx formations, when we do not run the engines at its appropriate fuel ratio or equivalence ratio. Then we will move on to, basically for all the 3 cases we will see that what type of reactions are very important and for which it leads to this formation like CO or NOx. Another important concept that we are also going to introduce, that when fuel gets oxidized, how all the molecules of the fuel gets burnt, and the way how they have been formed. And when we say oxidation of the fuel, and we are our main concern is the fuel is nothing but your hydrocarbon fuel. So, basically speaking, till this point of time whatever we have covered, we will try to look into the practical glimpses that which are normally the conventional issues nowadays, to look into the reaction mechanism of practical systems. Just to give preliminary introductions, we all know that we have global and elementary reactions, and when a global reaction we see fuel and oxidizer as a whole, and it gives combustion products, and this rate at which the fuel gets consumed is a function of the global rate coefficients and concentrations of fuels and oxidizer. So, based on which we can define the order of reactions. Now, and these and when you look into the elementary reactions, so the elementary reactions, if you see, fuel gets dissociated, oxidizer also gets dissociated, and they form some kind of elementary reactions. They categorized as unimolecular, bimolecular, termomolecular reactions. And in fact, these reactions are nothing but the chain initiation reactions, chain propagation reactions, and also chain termination reactions. So, through this process they are not seen as a globally, but they are formed during the reactions, and also they are also destroyed during after the products have been formed. So, and they are called as elementary reactions. So, our tendency is to find out in this lecture that what are the elementary reactions that are being formed in various reaction mechanisms, and we will in particular we will be discussing about H2O2 systems, carbon monoxide oxidation, nitric oxide formations. These three are important. And in particular, when you look at hydrocarbon fuel combustion with air, we will have two cases. One is stoichiometric cases, where CO2 formation and H2O formation is quite natural, but when we deal with the non-stoichiometric situations, either the fuel can be rich or lean. So, based on that, the formation of CO, O2, H2 and N2 also becomes predominant, and to some extent when the temperature is very high, this N2 can also break and they can take part the formation of NO. So, this is the background of these today's discussions. Now, even if you look at the discussion points of earlier, like one case where methane propane air mixture gives the major products of combustion as CO2, H2O, O2 and N2. So, they are those things are formed during lean combustions, and you can see these concentrations of all the components or species, they vary with equivalence ratio, and also their mole fractions sometimes increases, sometimes decreases, and one point of time they reach a maximum. And in addition to that, when we have lean combustions, we reach we can plot the adiabatic flame temperatures, where we can ensure what is the maximum temperature that we can achieve during this methane air combustion process. Now, when you move on to rich combustion process, the same mole fractions are also important, or they are also formed. Apart from this, when you have rich combustions, you can see the formation of O, CO, OH, NO, then oxygen, and all these things are formed, and their concentration varies with when we increase the equivalence ratio. Now, the question arises, why these are formed, what is the mechanisms, and when these are formed, I mean from where they started arising, and in fact all these are radicals, they form in between. Sometimes they come out as a product and sometimes they do not. So, the our point of discussion today will be that how this for the formation of these components during a combustion process, what are the elementary reactions that accelerates these formations, and if at all they are formed, what is the condition of the fuel in terms of its equivalence ratio, whether it is a rich or lean, first thing. Second thing is that effect of temperatures, because when the reactions, when the products are formed, when the temperature is increased, then effect of temperature has to be taken into accounts. So, these two things are very basics for the reaction mechanisms. Now, first reaction that we are going to discuss, and it is very common, that hydrogen and oxygen reaction systems. We all know that hydrogen is a fuel nowadays, and also it is a green fuel, and oxygen is oxidizer, and when they are closely related, when they mix, they also form water, which is a friendly liquid and it is used for day to day life. And also in some situations, when these hydrogen or oxygen they mix, they can behave in explosive manner. So, the control of hydrogen and oxygen is very vital, because it is mainly used in the rocket propulsion systems. In a rocket propulsion systems, usually oxygen tanks is being carried out, and hydrogen tank also is being carried out, and they are kept in a liquid form, in liquefied form, so that we can have a higher density. Now, if at all they need to be stored combinedly, then under what circumstances they behave in a friendly manner, and other circumstances they behave in a explosive manner. So, this is the very basic bottom line of these H2O2 systems. So, if you look at closely these H2O2 systems, the many reaction species, and in particular there are about 8 important species, and these 8 species are hydrogen, oxygen, water, OH radical, oxygen atom, hydrogen atom, HO2 is a another compound, and H2O2 the combination system. Now, out of this H2 is HO2, when HO2 is formed it is very friendly, but these radicals when they form OH, OH, and they are actually chain initiation or chain propagating reactions, and they keeps on spreading as and when they get a very good environment, I mean required, that is required pressure and temperature if they get, they make their chain in a growing manner. So, the reaction during these phases, the changes of reaction pathways, which is a function of temperature and pressure, it can result in various regimes of explosive and non-explosive behavior. So, let us understand what are these, how it can form, I mean in H2O2 system what may happen. There are two important case happens during the initiation process. If the temperature is very high, then we will have this kind of interactions. H2 in a third body with high temperature collision, they can break as H plus H. But if it is temperature is not too high, then H2 and O2 they will not break, rather H2 and O2 they will combinedly try to form HO2. And this HO2 is a friendly, but H is not. So, what it does is this H, and depending on the temperatures OH and OH radicals, they keeps on increasing the chain, and in this manner, I mean in particular H can plus O2 can give O plus OH, and even in some cases you can produce, you can find out OH again can react with H2 to form water, and O again mixing with H2O can give OH. So, these are chain chain reactions that keeps on happening if the pressure and temperatures are friendly, and these things keeps on happening till entire fuel or entire H2 is consumed, and at one point of time we will have a chain terminating reactions. And this chain terminating reaction, when you see, either you can get in the form of water formations, or we may have oxygen again directly, and there is also formation of hydroperoxy radicals and hydrogen peroxide, and in fact this HO2 and HO2 and H2O2, these are nothing but your hydroperoxy radical and hydrogen peroxide. When they form, they try to stop the chain. I mean we can say that reaction is a complete process, and there is no further, and they are not inactive. So, when such a situation arrives, then we can say the HO2 formation is active, and again this HO2 sometimes if we get a very friendly environment, it again can start other radicals as well. So, what I am trying to say, all these reactions are dependent on pressure and temperatures. Now, let us see what is the effect of pressure and temperatures, and this particular figure talks about the pressure and temperature plot in a H2O2 systems. I mentioned earlier that in some environment of pressure and temperature conditions, H2 and O2 can stay together, and in other situation they can behave in a explosive manner. So, we will categorize in two philosophy, one is no explosion, other is the explosions, and we will try to see under what conditions we will have explosion and under what conditions we will have no explosion. Now, if there are explosion, which reactions are predominant? If there is no explosion, why it is not, why there is no explosion? So, such things needs to be answered in this plot. So, what has been plotted in y axis we have pressure in millimeter of Hg, and the pressure can starts from 1 millimeter of Hg, means which is almost a vacuum conditions, and you can go up to 10,000 mm of Hg, and somewhere we can say somewhere you have 750 mm of Hg, we can draw this line. So, which is normally called as atmospheric. Okay. So, if you draw, this is your atmospheric line. Now, in this atmospheric line we can say we do not cross, we are mostly in the no explosion zone. And let us see what is its effect of temperatures. Now, when we look at temperatures, typically the behavior of H2O2 system comes when the temperatures range is between 400 to close to 580 degrees centigrades, and at 1 millimeter of Hg we can store the hydrogen and oxygen systems at 580 degree centigrades. So, this is what the summary is. Now, let us see how you look at this graph or how you interpret this graph in a so that we can understand the chain reactions and the chain terminating reactions, why this chain reaction happens, how it initiates, how it propagates, and finally how it terminates. So, normally when it terminates, it forms with HO2 or H2O2, and when it does not, when it have chain reactions, it tries to form OH, OH or O, all these things. And why this system is important? Because it is mainly required for rocket propulsion systems. What we are looking at the temperature and pressures corresponding to initial charging conditions of in a spherical vessel which contains reactants. Like in a spherical vessels, we are putting hydrogen and oxygen and try to see try to see the thermodynamic behavior in terms of pressure temperature plot. Now, imagine one particular case, like we are looking at 500 degree centigrades. Now, and I am just explaining at one particular case when you are looking at 500 degree centigrades, and I am just drawing a vertical line. What it means is that if I go along this line, we can have different pressures, okay, and we can see a curve. Is a nature of is typically a sinusoidal curve, and this 500 degree, if you draw a vertical line, it cuts this pressure axis, or it cuts this curve at different pressure values. So, let us start the first line. That means we are looking at a vertical temperature at 500 degree centigrades with lowest pressure of 1 mm, and we are going up. So, what do we see now when we are going up from 500 degree centigrades to this point? So, it meets the first curve close to somewhere 1.5 mm of Hg. That means this pressure corresponds to 1.5 mm. Now, in this zone, if you look at the hydrogen and oxygen systems, we see there is no explosion. So, what it means, why there is no explosion? Because in the initial step, it is just an initial step, the radicals are about to form, but they have not started the chain sequence, and when if at all they are formed, and these reactions when they keep on propagating, and finally they get destroyed in the walls of the vessels. So, what it means that when these radicals whatever form, they are absorbed as products in the vessel wall or geometrical vessel wall. So, why is a spherical? Because it all depends on the geometry how you are storing. So, these wall reactions break the chain, that means when the reaction and goes and hits this wall, they normally break the chain. I mean they are basically the culprits of the breaking the chain. So, that means the reactions is not further initiated, and also the reaction do not get a good environment to proceed further. So, that is the reason there is no explosion till this point. Now, moving further in same line, if you go vertically, we will find the second limit of the curve, and this refers to as 50 mm of Hg, and during this particular phase we can see that there is a big explosion. And why there is a big explosion, you can see that is mainly because the formation of O atom, OH atom, and this chain keeps on propagating, and when they keeps on propagating, the walls of the spherical vessel is not sufficient to withstand or stop their propagations, and these reactions dominate over the wall reactions. I mean that means wall cannot absorb further. So, because the wall cannot absorb further, it try to explodes. So, it means that when your storage medium is at 500 degree centigrades, any point above from 1.5 mm to 50 mm of Hg, there will be an explosion. That means we cannot store H2O2 simultaneously in a spherical vessel. And you can here in a generic chain mechanism, the increase in the pressure will result in higher concentration radicals in a linear fashion, and the reaction rate is increased geometrically. Now, moving further in same 500 degree line, if you go vertically till above 50 mm of Hg to up to close to 3000 mm of Hg. So, during this point you can see there is no explosion. So, what it means? So, during this phase, during this region, we can store them without any explosion, because during this phase the chain mechanisms try to terminate. Why it try to terminate? Because it gets suitable pressure and temperature regime for which the formation of HO2 or H2O2 becomes possible, and when they form, they are typically relatively unreactive, and we say that the chain is going to, and the chain reactions are almost terminated, and the further branching is not possible, and because of this reason there is no explosion, and this will go on till we reach the 3000 mm of Hg. So, we say there are three limit. First limit is, and three limits, and all are on 500 degree centigrade line. One limit is 1.5 mm of Hg, second limit is the 50 mm of Hg, third limit is 3000 mm of Hg. Now, but again beyond 3000 of mm of Hg, in the same temperature line, if you go, there will be further explosion. So, what we can say that when the formation of HO2 or H2O2 is predominant, then they try to the radicals effect is no longer severe, and the reaction try to settle down, and there is no explosions. So, this is the complete philosophy of hydrogen oxygen reaction systems, and in fact it the models needs to be developed to study the combustion phenomena, and experimentally it is very vital that you should know that what pressure and temperature we should store H2 and O2, so that it will not explode. The next reaction mechanism is carbon monoxide oxidations. Carbon monoxide normally forms when we do not have the stoichiometric hydrocarbon fuel oxidation with air. You can see that when there is in a non-stoichiometric case, we will have CO2 and CO formation simultaneously, and because and if at all this has to be, and again we have hydrogen also and nitrogen also. Now, this hydrogen and also we have water. So, what happens if you look at closely hydrocarbon monoxide emissions, the process of CO can form or when you say when a CO reacts with water, it gives CO2 plus O, but it is a very slow process, and the process, and we can say but very slow process, but it gives a oxygen atom, and we can say it is a radical, and but this radical will create a hydroxyl radical, and that is where the chain branching starts. And when it forms the OH radicals, you again react with CO, it gives CO2. So, it is a key oxidation reaction because that is the oxidation process. So, what we see is that directly with CO2 this is a slow process, but through a route of hydroxyl radicals it is a fast process. And again during this chain propagation reactions, there is also another feedback oxidation reactions where H will also give O2, it will give OH and O2. OH and O2 will initiate this hydroxyl reactions, O will initiate this chain initiation reactions. So, this process keeps on happening. So, the combined effect is that the how you are going to do the oxidation of carbon monoxide. Either to do that we must do through the HO2 or H2 route, because they have tremendous effect in enhancing the oxidation rate. The next important mechanism is oxides of nitrogen formation. Typically we call this as NOx. Now, this NOx formation is also equally important in a combustion process, both in rich combustion and lean combustion. And why it is more important? Because this NO formation has a important contribution to air pollutions, and mostly we should avoid this NO formation. So, if you look at the combustion process of hydrocarbon fuels, the nitric oxides or NO2 is formed by three chemical important mechanism or routes. So, you can say the NOx formations comes by three important mechanism. First one is a thermal mechanisms, or we in a scientific way we call this as a Zeldovich mechanisms, and this thermal mechanism we will recognize only when you have temperature is above 1800 degree Kelvins. It means that during a reaction process, when the temperature is above 1800 degree Kelvins, thermal or Zeldovich mechanisms dominates. But this thumb rule is also not true, because we have seen in our previous slides that when we have propane air mixture combustions, NO is formed throughout all the equivalence ratio. Then that even the NO is also seen in the lower equivalence ratio, but still the temperature is not too high. So, for that Zeldovich mechanism or thermal mechanism is answerless. For that reason, another mechanism that comes in what we call as Fenimore or prompt mechanisms, and this prompt mechanism arises, and it is a short time scale event, and it is answerable for rich mixtures for which equivalence ratio less than 1.2. But still this is also not possible, because most of the combustion process when you do the equivalence ratio is maintained between 0.8 to 1.2. So, both Fenimore or prompt mechanism and Zeldovich mechanisms, they are sufficient to answer both the cases. But there are some situations at low temperatures, if at all, and during lean mixtures less than 0.5, if there are NO formations, we call them with their they call this as a NO2 intermediate mechanisms. So, this is the three ways that NO can form over wide range of equivalence ratio with respect to temperatures, low temperature, medium temperature and high temperature during a reaction process. So, as a rule of thumb, we do not consider Fenimore, we consider the thermal or Zeldovich mechanism only when the temperature is very high. When the NO formation happens in a short duration time scale, answer will come from the Fenimore or Prompt mechanisms, and of course, it is for rich combustions. And when you talk about lean mixture and low temperatures, N2O mechanism plays a crucial role. Now, let us see how they behave. So, I mentioned this again, I revisit this slide again. As you can see, over wide range of equivalence ratio, we can see the formation of NO is throughout all the equivalence ratio. Even your adiabatic temperature is almost more than close to 2278 Kelvin. At that point, it is quite obvious that we will have thermal or Zeldovich mechanism. Now, let us understand the first one, that when this thermal or Zeldovich mechanism happens, what are the elementary reactions? First thing is that O, oxygen will react with N2, it can form NO plus N. Again, this N can also react with oxygen to give NO and NO plus O. And if we have radicals in these systems, NO can also react with OH, that also can give NO. So, NO formation can happen in three ways, and the rate at which they form, it all depends with respect to the rate coefficients. So, these are some sample expressions that talks about how NO formation comes into picture through these three different routes. Then next mechanism is Fenimore or Prompt mechanism. So, here when you look at here, you have to see that this formation is mainly the equivalence ratio up to 1.2, and when I say equivalence ratio of 1.2, and if you try to map this for a combustion process, you can correlate that they are in the zone of laminar premixed flames, and during this process there is a formation of hydrogen cyanide, NCO, and these two we call them as a chain initiation, chain sequence reactions, and these reactions finally gives rise to NO formations. So, it starts with CH N2 with this, then we will have N formations, and HCN again reacts with oxygen and it will give NCO. NCO will give nitrogen oxide, and NH, and NH will react with N plus H2, and finally N plus OH gives NO. So, when this NO formation is there, and through this in a sequence process, through and chain initiation and chain sequence process, and because of these regions we say that, and all these things happens in a very short duration events, maybe in a milliseconds or less time scale. So, it is called as a prompt mechanisms. Another important consequence is that when we have higher equivalence ratio and side by side temperature is also high, then we can say Zeldovich mechanism can couple with Fenimore mechanism. When both the mechanisms happens, this N plus NO will give you N2 plus O, means in fact on a Fenimore mechanisms, if there is a Zeldovich mechanism which dominates, it tries to destroy the NO formations. I also mentioned that why it is called as a prompt NO mechanisms. Many times the presence of O and H2 atom, we call this as a super equilibrium conditions. So, because of these reasons, the formation of NO is accelerated. Now, moving further, in the third category we have N2O intermediate mechanisms, and in these intermediate mechanisms where O plus N2 gives N2O plus a third body, and then this N2O can react with hydrogen to form NO and plus NH, and O plus N2O can also give NO plus NO. So, and this typical situation happens, we call this as a fuel lean conditions at low temperature conditions. And there are some situations when NO formation is initiated through a solid fuel, because if you look at a typical solid fuel like coal, they have nitrogen in their molecular structures, and when you have nitrogen in their molecular structures, and typically they are by 2% by mass, and they form rapidly. If they get a very friendly environment, they form rapidly through this hydrogen cyanide or ammonia route to form NO, and this will fall under the prompt NO mechanisms. So, if you look at the complete NO formation analysis, if you have a hydrocarbon and fuel, and from any route if you come, this is a complete process that talks about all the three mechanisms. Either the NO formation can happen with H or OH radicals, or through HCN, or through HNCO, NCO. So, this picture gives the complete picture of NO formations at different temperature and pressure conditions. And to give another kind of emphasis that how this NO formations affects in an atmospheric situations, we can say that in the atmosphere nitric oxide ultimately oxidizes to form nitrogen dioxide, and which is more important to production of acid rain and petrochemical smog. So, you can say NO plus HO2, it can give NO2 plus OH. This is the NO2 formation process, and NO is also gets destroyed through reaction with hydrogen. Then this NO2 also gets destroyed through oxygen, and this combination process happens in the atmosphere itself. Many times when this formation of NO becomes NO2 becomes significant, it leads to acid rain or petrochemical smog, which is not a desirable with respect to atmospheric viewpoint. And we can say these formations happens mainly due to the radicals like HO2, NO2, and of course the atmosphere has different temperature zones, low temperature to high temperatures. That effect is also very significant at what altitude, at what locations where this NO2 formations happens. And in the last, I will just try to explain the concept of oxidation of fuel. In fact, we have also seen the many combustion reaction mechanism processes, but here the oxidation of fuels comes on in a very complicated process. A complete understanding is required, but I will just give some introduction that when you say oxidation of fuels, we are essentially looking at the hydrocarbons, and maybe for higher paraffins and alkanes, for which we can say chemical formula Cn and H2n plus 2, they are characterized in 3-step process. In the first step, fuel molecule is attacked by radicals to form an intermediate, which is in the olefins or hydrogen. Second one is the intermediate process that oxidizes to form CO and H2O, and third one, the CO and remaining H2 they are oxidized to form CO2 and H2O. So, this is the 3 oxidation process, and in fact, we are not going to details, but a simple hydrocarbon is nothing but a methane, and it is a unique hydrocarbon, and it is a less reactive, but even though it is less reactive, it consists of 277 elementary reactions with 49 species, and 0.1 second residence time of each species. That means it forms and then gets destroyed. So, the residence time is of each species is close to, on average residence time you can say about 0.1 seconds. And since methane has also tetrahedral CH bond energy, which is exhibits which gives a very unique combustion characteristics. It has a very high ignition temperature, low flame speed, and it is not reactive in terms of petrochemical smoke chemistry. That means methane, if you are using, it is a good fuel for with respect to atmospheric viewpoint. The reaction pathways for this methane can be modeled in two temperature range, which is one is mainly less than 1500 degree Kelvin, other is the high temperature oxidation, which is higher than the more than 2200 Kelvin in a well stirred reactor with homogeneous isothermal environment. So, for more details we can refer the books. We are not going to details more details on this reaction mechanisms, but in summary what we can say that the mechanism of oxidation of fuels is a very complicated process involving many number of reactions, and it has to be modeled in an accurate manner to find and reaction kinetics has to be included simultaneously, and such reaction mechanisms we call this as a chemical reactor, which will come in the subsequent modules. So, with this this is the complete description about this model and module, that is chemical kinetics. So, before we close, let us understand some one of the basic problem which we have covered in our earlier lecture with a concept of EGR. So, EGR why we have introduced here, because it has a definite link with nitric oxide oxidations. Normally exhaust gas is recirculated in the engine in an IC engine to control the NOx formations. So, through this problem we will try to see how much EGR is advisable to be circulated into the engine for an efficient combustion process. So, let us understand the problem first. Theoretical maximum combustion temperature in an engine while burning an isooctane with an equivalence ratio of 0.833 is 2400 degree Kelvin. Now, at this temperature this NOx formation is quite important. So, it is reduced to lower these temperatures to 2200 degree Kelvin. What we do is instead of sending the exhaust gas directly to the atmosphere, we recirculate into the engines. So, we call this as a exhaust gas recirculation into the engines. Now, question is how we have to find out the percentage of EGR, how much percentage we should advise. And of course, there are some temperature you need to look at, all the data has to be referred at these temperatures. So, exhaust gases are expected temperature is 1000 degree Kelvins, and we also need to find out the product enthalpy of formation for the products at these temperatures. So, to solve this problem, first thing what we should attempt is that what happens for an isooctane conditions, what an equivalence ratio of 0.833. So, 0.833 means it is a lean combustion, and it is, if you can closely find the value, it is 20% excess air. Now, if you do that, then reaction could be C8H18, which is isooctane, plus 15O2, which means it is 20% excess air, plus 15 into 3.76 N2, and that gives 8 CO2 plus 9 H2O plus 2.5 O2 plus 15 into 3.76 N2. Now, we have to write another equations when by incorporating EGR. So, we do not know how much exhaust gas is going to be recirculated. So, basically it has effect of only effect of for with respect to NO. So, we have to revise this equation with EGR. So, we can rewrite this equation as C8H18 which remains as it is plus 15 O2 plus 15 into 3.76 N2. Here we will add some X N2. We do not know when the exhaust gas is recirculated, it comes with in the reactant side again. So, how much we are introducing N2 into this system, we do not know, and it also should give 8 CO2 plus 9 H2O plus 2.5 O2 plus 15 into 3.76 plus X times N2. So, this reaction needs to be handled properly to do that. So, we have to recall these equations, enthalpy of reactants and products, that has to be matched. We can write this equation Ni into HIFO plus delta H I, that is for products, and this product is at 2200 Kelvin, and that has to be matched with reactants summation of Ni HFO plus delta H, and this is for reactants, and we are looking at the reactants have some this data to be 1000 Kelvin temperatures. So, the formation of these things we need to do that. So, for each case we need to find out, and we have to note the values 1 at 2200 Kelvin. So, this enthalpy of formation value, first thing for CO2 product side we have CO2, we can write HFO minus 393,522 and delta H is equal to 103562. Then we have H2O, for which this number is all these units are kilojoule per kilomole. That is minus 241826, delta H is equal to 83153. For O2, HFO formation is 0 because it is stable gas, but delta H is 66770. Then we have N2, HFO is also 0 stable gas, and delta H is 63362. So, this is for products, and for reactants we have to note down this value at 1000 Kelvin for N2 and rest at 300 Kelvin. N2 means that 1000 degree for EGR. So, noting this value for C8H18 HFO minus 259280, delta H 73473, O2 HFO is equal to 0, delta H is equal to 12499, N2 HFO 0 and this number is delta H is 11937 and this value is at 300 Kelvin and at 1000 Kelvin this delta H value is 21463. So, this 1000 Kelvin will refer to component X. So, based on this formulation, by inserting this value we will have a big expressions, but by inserting the value we can solve these equations with for X as unknown and that X is 16.28 moles and this when converted to mass. So, 16.28 into molecular weight of N2 28. So, this gives 455.6 kg. So, means this much kg of AGR is being has to be circulated to bring down to this temperature. So, correspondingly we can find out what is the mass of air, which is 15 into 4.76 into 28.97, this many moles, molecular weight will give 2070.6 kg and mass of fuel, not mass flow rate. So, it is a mass flow, we can say 1 molecular weight of fuel 114 1 mole into molecular weight. So, it is 114 kg. So, ultimately we can find out what is the total mass. M is equal to Ma plus Mf plus MEGR. This is 2640.4 kg and we can say percentage is GR. So, this number would be 455.6 divided by 2640.4. So, this is about 17.3%. So, basically speaking, normally when exhaust gas is recirculated in the engines, its typical number is limited within the 20% of AGR. Then only we can get the better or effective utilization of energy in the engines from the fuels. So, with this I conclude this lecture for today. Thank you for your attention, and also we completed this module that is chemical kinetics. Once again, thank you for your attention.